Thank you for the perfect introduction from the host and Professor Tang. From the host and Professor Tang, and let me just share my screen. Okay. Entire
Yes.
screen. I hopefully you guys can see my screen now. Yeah.
Yes, yes.
Okay. So, thank you for having me here today to talk about how RL enhances spatial understanding. So basically, my previous works were focusing on how to introduce geometry pure into generative modeling, and some of these works have significant real-world applications, such as 3D foundation models. Well, let's get started my talk with the quote. Is the usual quote that from Rich Sutton about the beta lesson. So, one thing that should be learned from the beta lesson is the great power of general-purpose methods, of methods that continue to scale with increased computation, even as the available computation becomes very great. The two methods that seem to scale arbitrarily in this way are search and learning. So, from the beta lesson, we can at least know that two of the most significant perspective is try to scale with two of these methods, which is search and learning. And we will gonna introduce these methods specifically, mostly search, which is in context searching, chain of thoughts, some sort of methods in later of this talk. So, just look at this diagram. We can somehow figure out there's a significant trend that shifted within these 3D foundation models, 3D models. That is, from specialized model and more going to the weight of the foundation models. So in the previous works, we are focusing on a specific perspective of the 3D intelligence. For example, we try to develop a 3D dense captioning model to try to understand the 3D scene, and we try to develop a feed-forward reconstruction model to help us reconstruct the scene, just given some context of images, such as like sparse multiple view or dense views. And these things has been evolved into a generalist framework, which is you have a certain model that can somehow capable of handling different tasks. For example, we have developed a 3DR1, which is the main topic of today's talk, that a foundation model can handling various downstream tasks of the 3D scene, and helps the embodied agent to understand what's going on surrounding it. So there are also other kinds of foundation models. For example, we developed NavR1 to help the unmanned vehicle or a robot dog to navigate into a unseen or zero-shot scene. And we also have the VLA R1 which is also a foundation model that enhanced by RL to manipulate ARM-type robot, so it can approach to an object when they have some sort of affordance, and they can predict the trajectory for the ARM robot. So we just talk about some specialized models, so we can start from there. So one of the core, let's say core research topic for real world embodied agent is to efficiently reconstruct the scene. So back in like 2024, before 2024, we have SDF, NERV, GS, those kind of 3D representation. So what's the real bottleneck is that given a certain context view or a input multiple views, it takes significant time for us to reconstruct the scene with no matter it's a point model or a novel view synthesis, but they all takes a certain amount of time. But for embodied agent, we don't have such computational cost for us to like waiting until the scene has been fully reconstructed. So how to handle that? There are so many ways on efficient AI currently working on these kind of problems. For example, you can see nowadays or recently there are quantization method, there are token merge method, there are distillation methods such as like fast VGT, those kind of methods, but they ignore the geometry inheritance or the geometry nature of those kind of views. Is that we can somehow clustering those views and we can perform a latent token merge within those views. So if we can find a view that represents a surrounding cluster, we can use that kind of geometry knowledge to perform token merge instead of we just find a theoretical or strategy within the attention score that's somehow is not close related to the geometry. So that's what ZPressor did. Like ZPressor is a algorithm or is a model that we can select the anchor views from their geometry, and we assign other views into that corresponding group. So it's basically a clustering, but without relying on any supervised cluster method. And we can merge those kind of support views into that anchor views in latent dimension. So so later on we can perform a more efficient reconstruction because the transformer context is limited. If we can reduce those token lengths, we can somehow reconstruct it more efficiently. So that's how you handling sparse view or dense view reconstruction within a feed-forward framework. So here's some of the example of ZPressor. You can see with our method, not only we can reconstruct the scene more efficiently, we can somehow remove those kind of floating point and result with a better, cleaner normal views. So that's what the ZPressor has eventually been accepted to NeurIPS. And another perspective is that we just mentioned geometry pair, and geometry pair really matters for feed-forward reconstruction method. So currently, like 99% of the feed-forward reconstruction model relies on a certain type of geometry pair, which is steps. So you have some sort of relative depth prediction model, for example, like Unimatch or depth sensing V2, and they take one of the images and give you the depth prediction. It's not matrix depth. It just tells you what's the relative depth position between those kind of objects. So they kind of rely on these kind of problems, but relative depth is not always accurate. And we revisit these kind of problems, and we somehow figure out that, okay, there's a way that we can enhance those geometry pair by leveraging an existing point models. No matter you have a traditional structure for motion or the recent feed-forward models such as VGGT, they can always give you a strong feedback on geometry. So the most easy or the most simple yet effective way is that you have one of these point models and you predict the point of the scene based on your input views, and you somehow design a loss between your Gaussian, like your Gaussian model is your main model, right? Is your what you want between those predicted Gaussian and the predicted points. So how we can do that? How we can design those kind of loss is basically a very simple way. Is you can design a point prediction by designing a loss based on transfer distance. So we introduce a loss named PM loss. Is a regularization loss based on a point map model that's predicted by your point models such as VGT, and we design this kind of regulation loss based on transfer distance. So the point model itself probably not that kind of accurate, or at least from a depth perspective, it's not that kind of accurate compared with your depth model, but it can gives you a enforce, or let's say forcing a more geometric smoothness. And especially this kind of problems has been leveraged, has been tackled when we approach to the edge of the object, for example, the boundaries. Those the most severe problems when it occurs, that is floating Gaussians, like Gaussian points are floating around the object. So we kind of tackling that problems, and you can see those these are the demonstration that that's a basic depth sphere model called depth. That is a depth enhanced sparse view reconstruction model based on the NV splat. And if we train with our PM laws, the PM laws is basically point model laws, so it's a very simple name. And you can see the floating point problem of the Gaussian model has been significantly addressed with our training strategy. So that tells you a significant thing is a geometry period that really matters. So we should not omit those kind of period knowledge when you develop a specific models. So another point of perspective view is that we challenging the existing 3D foundation models framework, that is per pixel alignment. So most of the models currently is per pixel prediction. That is, you have, so for each view we have a single Gaussian that represent those kind of views, and we perform per pixel prediction, and eventually we perform a Gaussian merge into a whole Gaussian that we do rendering. We can have the null views of these scenes, but the main problem is occurs during these Gaussian merges. You know the per pixel prediction is not always accurate, so there are always going to be some errors within those predictions. And when you doing merging, there will be different layers that is not perfect aligned, and result in a render Gaussian is like they have different layers. They should be aligned, but they're not. Those kind of method existing with the inheritance of the current method, which is the per pixel alignment of the feed-forward Gaussian. So we challenge this kind of question, and we think if they perform a voxel aligned prediction instead of a per pixel prediction, is this problem going to be solved? The result is somehow yes, from some perspective, yes. So instead of we do a per pixel prediction of each view, we perform a voxel alignment. So we perform a feature unprojection of our image feature, like image bending, and we perform a refinement. That's basically some sparse convolution, and result is we have a voxel aligned representation. Let's say we call it volumetry representation, and we don't need to do Gaussian merge anymore. We just do a voxel aligned prediction to result the Gaussian we want, and we do perform null view synthesis, that's rendering, and the result is the null views we get is much more clear compared with the conventional per pixel prediction. So that's the detailed pipeline, is that we extract the 2D feature of each images that's every model views that did, right? And we perform we calculate their cost volumes based on their disparity, and we result with a voxel feature. Let's say that's a volumetry feature, and we have a sparse 3D coder to get our refined voxel feature we want. That's what we mentioned just here, the refinement part. And result is we don't need to do any Gaussian merge. We can directly get a Gaussian that is much more clear compared with the per pixel alignment. And after reconstruction, we can after rendering, you can see it shows you the similar results. Is that we don't have those kind of unaligned, not aligned or disaligned layers of the render views. So we just talked about the reconstruction perspective of the specialized method, and we're gonna talk about more about the understanding point, which is the main topic of our talk. So before we were working on foundation models, how we can tackling scene representation to understand what's going on around within those 3D scenes. So one way we tackling this problem is performing 3D representation learning, and when you're tackling a problem such as 3D understanding, there are always going to be multimodality knowledges or multimodal data. So one of the main modalities that you have those kind of images, or videos that represent your multiple views, or BV or exo views, egocentric views, whatever. And another modality is you probably have the 3D point, or let's say you perform a you have a laser that's scanning through your skin. Scanning through your skin, you can have the point model, and another important modality is text. So basically, you have two kind of different form. One is QA, the other is captioning. So basically, you want to know what's going on, what's the geometry relationship between those two objects, or can you describe the scene for me? Some sort of text. So the most easy way is that you're trying to align those kind of different modalities, and within a common embedding with the prior knowledge what we do in 2D space, which is contrastive learning. And we somehow leverage this kind of representation learning method into 3D, and we perform a 3D multimodal representation learning. That is, we have a point transformer that encodes this point into a point embedding. We have the original clip, let's say the bird-like encoder to encode the text, and if we can gather a certain amount of the high-quality data, we can somehow learn a good embeddings for those two modalities. So that's the core ideas of 3D COCA. And similarly, if we have a transformer decoder, which the most basic one, you can somehow, given your text prompt, you can have some response. So the response either give you the caption for the scene or answer your questions. So all you need to do just have a transformer decoder behind your encoder, behind your 3D clip. So that's the most simple way to perform a 3D representation learning. And since we gather a high quality data from existing human labeled data, for example, scan QA or NR3D, we can somehow perform our 3D representation learning within those data, and we came out a better results or better outcome compared with conventional label to cap method. And here's a demonstration that we're more aligned with the GT. So this gives us a hint. So what we can do if we train a very good very good 2D multimodal model that can give you a good 3D representation. What we can do with that? One way is that we can perform data-centric learning. That is, you can develop somehow algorithms that can help you filter out bad quality data. So you can probably achieve a similar performance or even better performance just by removing those kind of noises, and you can save a lot of computational costs with the data-centric learning. So we then follow the 3D COCA. We just directly use our pre-trained 3D clip as a data filter. So we design a dual indicator quality let's say DIQ model that select the most important data, for example, top 75% of the whole data, and we can get a better quality subset of the data, and we can then use those kind of data to train a new model to approach the full training. So that's the core idea of data-centric learning. So previously we need a human in the loop, right? Human in the loop process to help us clean up those kind of data, and if we have a good representation model, we can do it automatically. So DCC only use top 75% of the high quality data, can achieve a slightly better results than the full training model. That was really outstanding, because it tells you a sign that use data-centric learning method can help you remove those kind of noise data, and eventually gives you a better performance. So that's give you a sign that scaling, let's say in the bigger lesson, right? Scalable method is the most simple way to achieve better performance. But scaling is not taking all sort of data. It's taking high quality data to perform scaling. That's what we can get from the DCC. And so let's move from here. Like, what's the next for 3D foundation models? there are three essential problems that we haven't solved yet in the conventional methods. Is that the first problem is how can we achieve zero-shot generalizability across different tasks, given the domain knowledge gap between them? So you can see in the previous work, those conventional models is basically focusing on a specific task without any generalizability to another task which is unseen. That's the first problem. And what if the domain gap is huge between those downstream tasks, right? How can we bridge those kind of domain gap? So that's the first problem. And the second problem is how can we adjust a foundation model after the conventional supervised post-training when the outcomes are unsatisfactory on specific tasks. So given that we assume that we already have a foundation models, and how can we adjust it without giving too much energy, without losing too much energy, and we can somehow adjust these specific results when it's unsatisfactory. And then most importantly, how can we ground our foundation model in the physical world? We only perform our evaluation on benchmarks, and that's not what we do in Body AI. Is that we try to figure out real world problems, and how can we bridge those kind of gap between the benchmark simulation and real world. So that's what that's three questions we're gonna try to solve, and we're probably gonna come back to this page after we introduce the following works. So we have already had the kind of insight or knowledge is that scaling is important, high quality data is important. Then how can we achieve or obtain those kind of high quality data? One way is that we can have a human to perform human expert to perform the human in the loop process. Is that we have a sensor, we carry it around to a new scene, and we try to gather high quality data, then we perform human annotation. Well, that's effective, but it's really slow and expensive. So one way is that we can somehow synthetic high quality data by leveraging the great power of large language models. Although those kind of models are pre-trained in a word embedding in a languages, but we can retrieve those high-level abstract knowledges into our data annotation process to perform a to achieve a scaling synthetic data pipeline. So that's the main focus of the scalable way to achieve high quality data. So we design a chain of thought engine, which is use those large closed source language models to perform a chain of thought. So what is a chain of thought? Chain of thought is basically a searching method. So people always think about, chain of thought is boring and stuff. It's just a large language models that gives the large language models to predict extra tokens and to emphasize how it thinks within those black box. But actually, chain of thought is a searching method that they search in an in-context space. So what we want to do is that we want the large language models to search the not optimal, but a better solution to explain why we can get this kind of results. So we already have a high-level annotation from the original data. Why those kind of annotation has been concluded. So that's the meaning of chain of thought. So we leverage state-of-the-art closed source models called Gemini 2.5 Pro, and we somehow produce those kind of high-level chain of thought data and result in different kind of tasks. For example, there are color question within our synthetic data, there are location question, there are spatial relation, like is your chair beneath your desk or above your desk? Am I gonna able to put my chair beneath the desk? Is some this kind of question, and we result a very diverse and high quality, but not really large scale. Actually, it's just 30K, but enough for us to post training a 3D VLMs. So that was called Scene 30K. And let's say we want to address the first problem, that is generalizability. And how we can achieve generalizability is that your synthetic data should be diverse. It should be covered the common sense knowledge for all your downstream tasks, or even the tasks that you haven't seen yet, is still unseen. So the diversity is really important for your synthetic data. And 3D R1 has demonstrated a very strong performance across various tasks that shows a sign of generalizability, because we have those kind of diverse data. And once we train our model just simply with SFT, we can somehow get our the first version of the foundation model, that is pre-train as post-training on a diverse synthetic data with SFT. So that was the first stage. And with those kind of model, we can somehow handling various tasks. For example, 3D scene captioning, 3D object captioning, question answering, and the basic knowledge such as basic capabilities such as dialogue and grounding. And the most important is that the model has some sort of knowledge of planning and reasoning. People always distinguish these two. The reason why I pointed out with two blocks just follow the common sense of the community. But actually, planning and reasoning is the same thing. Basically, the same thing, two different words for the same thing. How you can evaluate your model if it has the reasoning capability is that you give him specific problems. Can the model give you a solution within a hierarchical planning? That's the sign of the model have the reasoning capability. And I just mentioned that the first stage is just simply SFT based on our diverse data. So that already gives a model or activate a model a reasoning capability. So there always let's say a misunderstanding in the community is that we need to use RL to activate a model to give the reasoning capability to a model, which is really a misunderstanding and somehow incorrect. The reasoning capability is obtained within a SFT, within a supervised fine-tuning stage, at least from our experiment. And the purpose of the RL is to adjust your model and to enhance your reasoning capability within a specific domain. For example, if your question answering is not satisfactory, you can perform RL on these specific tasks. So that's how RL works. So at least we can get a lesson is that reasoning capability is obtained in SFT stage, and RL is for adjustment. And that's what I'm going to say in next page, is that how can we adjust the model if it is somehow underperformed or unsatisfactory within a certain tasks. So the basic RL has really a various or diverse form. You can perform a traditional Q-learning. You can perform a traditional policy optimization, for example, proximal policy optimization, just short as a PPO. You can perform this kind of PPO can go beneath a form like if you have a human expert, they can offer you a feedback, and you use those kind of feedback in your RL policy. That was called RLHF, right? Reinforcement learning for human feedback. And if you have a foundation model, or let's say a large language models, to give you a feedback, that was called RLAIF, right? And those kind of techniques are really expensive and not really suitable for academia. It would cost a lot of money and time as well. So the basic way to perform an RL to somehow adjust the model performance is that you're designing some reward function and use that reward function as a feedback to adjust the model. That was called RLVR, a reinforcement learning with variable rewards. So during the first stage of experiment, we realized that three key perspective is very essential, and it's not that satisfactory for that model. So one is the perception. So the bounding box is not really accurate during SFT, and some the model can basically give you the local feature, give you the basic local quality, tells you where's your chair, where's your sofa, but bounding box is not really accurate. So how can we do that? The basic way is that you use one of your common matrices and as a reward, and and punish the model if it doesn't give you a precise bounding box, and give the model positive feedback when it gives you a satisfactory result. So this will help you boost significantly on the detection results. And another is that another problem we observed during SFT stage is that when you when you ask a 3D VLMs, for example, I have a picture that is in a bedroom, and the view angle is not really aligned with the for example, the question I asked, and I just asking a bear on the a toy or toy on the bed, but the toy itself is very tiny on the images, and the model is really confused. It cannot align your question with the perception, and always give you a wrong feedback. For example, they will say the bear is under the desk, or the bear is on top of the floor, which is incorrect. So why did this kind of things happen is that the model has misalignment between the text modality and image modality. They always give you a stuff that is hallucination. So that's really aligned with what Meta currently did, is that FAIR, they publish a series of papers to explain what is hallucination. Is that when the modeling tackling a long tail long tail proportion during their SFT, they're prone to be hallucinated. So tiny object is apparently a long tail problem within our SFT, right? We always training based on a major object within a image, and how we can address these problems. So we can somehow reinforce the semantic embeddings between the image and text modality, so make it more aligned. In the common representation space. So the basic idea is that we can introduce a clip reward, and clip can help us to make the those kind of two modalities much more closer, right? So we can somehow handling those kind of long tail problems and reduce the probability of hallucination. And the third reward, from my perspective, is the most important reward. That is format reward. People always ignore or omit the importance of the format, but it's truly a very significant perspective when you try to ground your 3D foundation model in real world. We're facing too many cases that is our model can perfectly address your problems, but the format is incorrect. that's basically two perspectives. One is during your SFT, your format probably not unified because your data sources varies, right? So some people labeling in one form, some people labeling in another forms, and you need to use your language model to refine your format. That's really a cost process. So during SFT, there are various different kinds of reward that cause you cause your model give like inconsistent reward. And second one is the limitation of the capacity of the model. So most likely our 3D foundation model is like 3B or 7B, right? It's very limited, and those kind of small models are more likely to produce an inconsistent format, and it's not good for downstream tasks such as robot manipulation. And for example, if you do a simple experiment that is adapt a vanilla Q1 7B to a VLA model, the model can somehow figure out how to predict the trajectory, but it always gives you a wrong format. So what we can do to address the kind of problem is that you give a format reward. You try to adjust the, try to let the model know which one is the format you want, and through reinforcement learning, you can make this kind of process more consistent. So format reward is really important for our downstream tasks as well, which I will introduce later. And within those, like with our RLVR processes, we can somehow achieve better zero-shot capability, as shown in the diagram. Is that the RL fine-tuning is way better in reasoning tasks compared with the SFT and RL zero-shot. Well, let's say that I just mentioned, RL can only help you adjust a certain task. So you can observe there are significant boosts in certain tasks such as dialogue, planning, reasoning, but little boost in the captioning, such as like those kind of 3D captioning matrices. That's really aligned with our assumption, is that RL can only help you adjust certain perspectives of the foundation model. And so after all of these systematic process, we can eventually get a foundation model called 3DR1 that capable of handling different kind of modality and different questions. So that's the first word. And there's some visualization results that can be shown. Here's an example of 3D dense captioning. Sorry, let me just move on. Here is an example of 3D object captioning. Is that you give it an object and let the model describe, and yeah, why there's always repeated, I don't know. There's a visual grounding tasks, and there's a QA task, and all good. There's dialogue. You basically talk with the VIM. There's reasoning tasks that set up certain questions, certain reasonable questions, and let the model give you the answer, and simultaneously give you the justification. And here's the planning: is that you give a specific task and let the model help you with a plan. And here's the zero-shot visualization. Okay, anyway, I have to mention that you can still observe some floating of the bounding box. Is basically because the visualization problem of the ARK kit, I think that was what we call. But it's not really the problem of the detection results. So it's basically the visualization results, and yeah. So all these scenes are zero-shot, which is the model haven't seen. It's unseen scene, and the model haven't been trained on these kind of 3D scene. So after addressing the first challenge, let me get back to the this page. Is that so? How can first and second problem is that how can we ground our foundation model into physical world? For example, let our foundation model to address specific real-world tasks such as navigation and manipulation. How can we adapt our model to these kind of tasks? So okay, let's move on to 3.1. Yeah. So the specific question is, what if we ground our 3D foundation model in 3D scenes? How can a reasoned approach to human level intelligence? Human level intelligence is a very mystery, or let's say clear but mystery part, is that none of our models currently is approached to human level intelligence. So we just try to develop our model to mimic the human way, but eventually it will, at least current stage, it will not achieve human level intelligence. But we try to develop our system into that kind of form. And this is inspired by psychology, is that the division of labor between system 1, which is a fast system, and system 2, which is slow system, is highly efficient and minimize the efforts and optimize the performance. That was proposed by Daniel, which is system 1 and 2. And this is a very classic theory of human level intelligence, that human divide its intelligence into two systems, and different system handling different frequency or different tasks, which is fast and slow. So for example, one classic example is that you can always see a chess player playing chess with simultaneously with 10 different students, and and then he can go one by one after another, just by simply put one of the chess into the panel, but the student itself need to think like 10 more minutes to find a solution to respond to the chess teacher. So in this case, it's very obvious is that the teacher itself is using a fast system that you use less labor to respond fastly, because to respond rapidly, because it doesn't take too much think for him. He plays chess every day, and there's not much effort to working on that. But the student themselves is pretty much working with a slow system, that is system 2. He need to retrieve all his knowledge, all his effort to try to figure out how to solve these kind of problems. So that's the difference between system 1 and 2. And this case also tells you that once you get familiar with the specific task, your knowledge has somehow shift from your system 2 to system 1. Is that you kind of put your rapid knowledge into long-term memory, and you don't need too much effort for playing a chess. Such as you can, through practice, you can improve yourself from a chess student to a teacher. So that's the basic knowledge we can get. And how can we develop this kind of system into the embodied agents? Is that we can develop our visual perception into two formats based on their frequency or based on their importance of observation. One of the most important is that their high frequency of updated scene. Like let's say you have a advanced radar that scanning through the scene and gives you a certain frequency, and is updated real time. So how you can process those kind of high frequency data is that you rely on a fast system, and the other step is that let's say the egocentric views, right? The real-time videos. Those kind of real-time videos are updated, for example, 30 FPS. That is, you have 30 frames within the seconds. That's a lot amount of data with highly redundant information actually, but with a very high frequencies. So those kind of knowledge should be processed within a fast system. And there are certain knowledges that when you pass through a key point, let's say the key point is that one chair within a center of the room, or a TV on the wall, which is very iconic and could be identified. Even you go back to the certain place again, you can immediately identify it. That's a key point. So this kind of knowledge is not being updated very soon. It's not within those. It's not similar to those egocentric views, such as updated like 30 frames within a second. So this kind of knowledge should be stored in the long-term memory and should be processed in the slow system. But this result, so we already know the high-level idea, but how we can design in the engineering perspective, you need to connect your model design with the real-world problem. Is that your model facing an efficiency problem, right? You cannot handling all of these high frequency data within the model, and you rely on those high frequency data, which means you have a super large context of the transformer, and the transformer will become really large and slow. So we design a fast and slow system. Is that we only use part of our models to handling those large contexts, or let's say high frequency information, but the whole system is a slow system. They only need to process the key information of this 3D scene. So that's result. The system in the diagram is NavR1. So NavR1 has certain level of feed-forward transformer. It's a plane transformer, and the whole system is a slow system. And within the later part of the transformer is the fast system. That is, we will give the fast system a large context information. And for example, the real-time egocentric view, the real-time depths, and the real-time 3D scene. So we only need to trade off efficiency within a certain part of the model. So that's the motivation for the fast and slow reasoning. And similarly, we already been mentioned in the previous slides that synthetic data matters. If you want to achieve diverse zero-shot capability, if you want to get a foundation model, you need high-quality, diverse synthetic data. So we do the similar thing. We synthesis 110K data for in a COT format, and we cover different kind of tasks. For example, we cover scene understanding tasks, we cover navigation tasks, and the navigation tasks can be developed into different formats. For example, what if we have a visual language prompt? What if we have an object goal, right? So there are different kind of navigation. We merge them together and result in a nav COT 110K. So we pre-train our model. We post-training our model with the 3R1 initialization, and we can get a NavR1, which is grounding in a 3D scene to perform understanding and navigation simultaneously. And we perform the similar thing for the downstream task. For example, if we can divide our downstream task into two perspectives, one is understanding and the other is navigation, we can develop different reward function for these kind of knowledges and for these kind of tasks. So that's the RLVR for NavR1. And eventually we can get a similar foundation model for navigation. So we can handling different tasks. If we put our embodied agent into a real-world scene, we can communicate with the embodied agent to perform embodied dialogue and reasoning, and even help us planning. For example, what if I want our robot from the start point to approach the door? Like how can it get there? So the VLM model can gives you a specific or detailed plan for approaching to the target, and eventually helps you navigate the robot to the target. And and one of the significant prospects is that you can see the navigation and understanding existing significant gaps. So we want our model to adapt to a new tasks without sacrificing too much knowledge of the previous tasks. We don't want a problem is that we train a NavR1 model. It gives the capability of navigation, but forget how to understand the scene. Well, that's what we don't want. So I'm not a big fan of understanding, or I'm not a big fan of navigation. We just want a system that can handling a thorough way. So we further evaluate our NavR1, and it shows that it doesn't sacrifice or trade off too many capability of understanding. It can still perform somehow. It still makes sense, right? A certain level of understanding. So why we can achieve this kind of problem? One of the most significant way is parameter efficient tuning. So what is parameter efficient tuning? I think everyone is familiar with LoRa, and people treat it as LoRa as the extra model. So they say, okay, LoRa's adapter is that we froze the backbone and we put we plug in one of the adapter to the model, and the adapter can learn new knowledge. Well, that's a most naive way to understand this problem. The most essential way is that the LoRa itself is a gradient. So when the new knowledge came up, we can store those kind of knowledge within those gradient. And this kind of gradient can be specified into different tasks. For example, in continuous learning, if we can keep update LoRa model and LoRa weight, we can learn new tasks. But in another perspective, such as recent really popular that is agentic memory, right? If we can store the memory into those kind of parameter, it can reproduce the exact same word of the agent. So the LoRa, the gradient itself is for different tasks. And we just perform the parameter efficient tuning with LoRa, with the fixed rank LoRa, to adapt the domain gap between the benchmarks and the real world. So that's how we do it. But LoRa itself seems to be very naive, because we just only adapt the fixed rank LoRa. So let's leave a question here. What if our domain gap is significantly large? What if I want my nav R1 model into a desert or into a underwater sea? So there's a huge gap between your knowledge base, your data source, and the real world. How can we develop a parameter efficient tuning based on that? So that's a significant problem we are going to talk about later. And here's the results. Yeah, and you can see we perform real world evaluation in different scenario and different scenes, and yeah, and also we can perform understanding tasks. For example, body reasoning, same at the real time, right? And why is this keep planning, right? The different planning, and if you want to interrupt with the for example, it gives you a satisfactory plan. I want to change my goal. You can tell the nav R1, say I don't want to go to black chair anymore. I want to go to the blue umbrella. It can adjust the plan, and in a some not really real time, but in a rapid way. So that's the capability that traditional navigation model cannot perform. And let's say the similar idea is for ARM type robot. It's just different optimized goal, or different different motivation, same motivation but different objectives. For example, for PLA model for ARM type robot, you are focusing on two perspectives. One is you want to have a precise affordance of the object. You want to detect the target object as precise as possible. And the second part is you want your trajectory as clean and as precise as possible. So those are the two main perspectives you care about of your VLA or of your ARM type manipulation. So the RL VR function will adjust it based on your objective, and specifically, so we can develop a trajectory reward and affordance reward to tackling those kind of downstream tasks. And most importantly, let's say, for robot manipulation, the format reward is always the most important one. You want your model to keep consistently produce the correct format, so it can compile within the robot motor, so it can manipulate in a correct way. If the model gives you the correct response but in an incorrect format, the robot don't know what to do. So in this case, format reward really plays a significant role. And here are some results if we leverage a similar idea to ARM type robot. And you can see it can handling different tasks. For example, they can tell the color. They can have a very precise affordance of the object, right? The yellow ball, not the white ball, and distinguish those kind of objects. If you analyze to a unseen objects, I think physical intelligence is the same thing. Like they have a pi series model, yeah, and what significant observation from both of us is that leveraging the power of I should stop. Leveraging the power of VLMs is that the model can handle better cases when the task is unseen. That is traditional imitation learning that you have a teacher to teach the robot. It cannot do, right? We can have a better performance on unseen problem. And we just leave a question is that what if the target domain and source domain have a huge gap? What if we want to adapt our robot into a completely different environment, for example, underwater scene? And how can we design parameter efficient tuning based on that? Well, apparently fixed LoRa cannot be work anymore because it have a limited capability. For example, if you have really low rank LoRa, low rank parameter, for example, rank equals 2, you have limited knowledge or limited capability to learn new environment. So how can we, based on that, how can we address these kind of problems? We figure out a really simple task that is matrix depth estimation with stereo region. So this is really traditional problem in underwater robot. So underwater robot is very different tasks that you can handle on a real world, let's say lifetime. That is daily life. That is you can use lidar. You can use really clear high resolution camera. You can use a TOF, right, time of flight camera or RGB camera to obtain the depth. But in underwater, all of these techniques are failed because sometimes the water gets polluted and and your TOF can only perceive a very narrow or very close distance. It cannot perceive a long way or long distance depths. That's one major problem. And your layer is failed because the reflection of the water is different of the air. So your layer is gonna fail. And one way to obtain the distance or obtain the depth information is performed by echo or sonar. Yeah, but echo or sonar is very expensive and needs time to prepare. And the second part is energy consuming. Okay, imagine you have a mobile robot that can only last for like 30 minutes within the water, and it wastes a lot of energy on the sonar, and your underwater robot haven't do the taxi and then it's run out of the battery. So that's what we don't want. So how we can obtain a matrix depth that can help our perform visual motoring or visual surveying, or let's say VLA, based on a relative or more precise depths. And we try a lot of problems. For example, foundation stereo anywhere, those kind of stereo depth estimation foundation model, they all fail in underwater scene. So we need a powerful and effective way to adapt our foundation model to the underwater scene. One way to tackling it is adaptive parameter efficient tuning. That is dynamic LoRa. So we want two objectives. One is we try not to forget the existing knowledge of the foundation model that can obtain a matrix depth. And second, we want to observe new knowledge, and we can adapt our similar capability of matrix depth into underwater scene. So dynamic LoRa will adaptively helps you obtain those the two kind of knowledges. So first you frozen your backbone, right, like the original LoRa, and it will contain your knowledges from your foundation model, and you concat, like inject different LoRa model into different layers, and let the model adaptively to adapt the rank of those kind of models. And the objective is the ground truth, right? It is the underwater depths in your data set, and the rank of each layer will adapt dynamically adjusted. So it itself will realize that, okay, this kind of knowledge I shouldn't be learned, and this kind of new knowledge I should learn, and the memory, let's say not memory, this has not been proved. The knowledge of within those LoRa can be dynamically adjusted. So that's how you adapt a model to a significant domain gap, like to address this significant domain gap. For example, from a foundation zero depth estimation to underwater zero depth estimation, and that's just from the beginning. We always said that synthetic data matters, like scalability matters, and how you can obtain this synthetic data or high quality data to support your post training in underwater scene is that we can leverage existing render engine. For example, we can use UE5 to set up some different scenes, and we compose the underwater environment into those scenes. And since it's in a simulator, right, we can always observe or obtain the ground truth steps. So we eventually develop a dataset called UW and water zero depth 40K to support our post training during the LoRa space, right? The LoRa procedure. So here's the evaluation, real world evaluation actually. Yeah, this is a sync. Actually, it's a sync, and we we have our robot. What's the robot called? Probably forget this. ROV, I think it's ROV, right? ROV robot into those sync, and we observe the ground truth is not really ground truth. It's actually structure from motion. So there's no way you can obtain the ground truth, like ground truth depths within the water scene. You cannot use a ruler to measure the depths. So what you want to do is that you want your matrix depth estimation as close as your structure from motion results. Because structure from motion is really time expensive, and you cannot perform a structure from motion on the mobile robot. It will run all of your energy. So what you need to do is that you want your zero depth estimator as close as your structure from motion results. So this is what we can get in a real world scenario. Let's say, yeah, it's pretty close. It's pretty close to the GT. Yeah. So that shows us two perspectives. One is dynamic LoRa is highly efficient, highly effective for adapting a significant domain gaps compared with previous traditional parameter efficient tuning. And the second one is high-level synthetic data really helps you to scale your model and adapt to a new scene. So keep. Okay. So there are other works that is keep working in progress in our lab. That is, we try to solve different downstream tasks. For example, how you manipulate your mobile robot. Now, currently we can only navigate our mobile robot in the unseen scene and to understand what's going on, but we cannot perform various action. For example, if we have a robot dog, how can we let the robot jump in an unseen scene or recovering from failure cases? Like, how can we perform that? Right now, we somehow explore this kind of problems, and I believe mobile robot, from our perspective experience, mobile robot is always much more harder than the ARM type robot, and the second part is we have already mentioned like 3 different feed-forward reconstruction method. Sometimes your radar, for example, is a very cheap radar, and it doesn't give you a perfect point model. And we want our robot to reconstruct the 3D scene in the real-world manner, so that we can leverage those point models, the reconstructed point, to better understand the scene. But this requires you develop an efficient real-world reconstruction model. So that's the second part we are focusing on. That is, reconstruct your scene within the feed-forward manner, but in a real-time fashion. And third part is everyone is working on that. Is video world model. Is that what if you have a perfect video world model that can predict the world state in the form of video frames, like, or a frame of chunks, right? Chunks of frames. So what if you have this kind of models, and how can it helps the embodied agent to address the unseen tasks is one of the main focus of video world model that we are currently working on. And here's just several examples of the mobile robot that we do. Sorry. So let's just let's just close my talk with the with the takeaways. So the first one is, do not abuse reinforcement learning for post-training. Use RL only to adjust foundation models output. So people consider RL as part of the post-training, and there's a lot of paradigm that currently use RL for pure post-training. For example, RL0, right? We have RL0 that a model fully rely on RL to to activate the reasoning capability. Which this is something that I don't suggest. Actually, RL is very expensive, and the correct way that we leverage RL is we only use RL for adjust a foundation model when it doesn't achieve satisfactory performance. And second one is synthetic data and data-driven methods are the key to achieve scalability and generalizability. That's what we learned from all of these experiments, and the bigger lesson is that we spend too much time on how to introduce geometry pure and artificial, perfect, beautiful artificial model to address a specific task. But eventually, those kind of problems are eventually be addressed by a foundation model that just use the most simple and easy way is that scaling your pre-training or post-training in a synthetic data. So we shouldn't ignore this process in nowadays, and eventually I believe that most of the problems can be properly addressed by a scalable method. And the third problem is third takeaway is work on unimodal LLMs that perform next token prediction will not achieve advanced machine intelligence or human level intelligence. If you're interested in human level intelligence, do not rely solely on LLMs. Instead, enhance spatial awareness in visual foundation models. Nowadays, all of the researchers are working on LLMs. LLM has significant impact to our community. It addressed problems very efficiently and effectively. That's a good sign. So people are always asking why LLMs achieve so much good performance nowadays from a current perspective, is that we somehow get into a shortcut to the human level of intelligence. The LLM is a pretty boring in mathematics. It just predicts the next token based on probability, and it doesn't do anything else. So, but it trained on the word space, the language space. Well, language itself, or the word itself, is the abstract representation that summarized with the human level intelligence. So it's naturally a abstract representation that can help to summarize what's going on within the world. So that's why LLMs is somehow into a shortcut to approach the human level intelligence. But it will not be the ultimate solution that we achieve human level intelligence. People always ignore the importance of visual foundation models. Is that the most high frequency data we observe is from our eyes and different sensors. For example, touch, like the fingers touch, right? And the audio listen those kind of sounds, not only languages but all kinds of sound. So these kind of foundation models in different modalities, apart from the languages, are the key point to achieve human level intelligence. And thank you for listening to this kind of long talk, but I hope my talk can bring you some probably some insights when we develop future works in spatial intelligence. Thank you.
Thank you. Thank you. So it's a little bit over time, but and some people drop, but I'm gonna